Hey everyone, welcome to another edition of the podcast, Healthcare's Missing Link, a podcast where we help you uncover those things that are stealing your best health. I'm your host, Dr. Mark Sherwood today, and it's my pleasure to introduce a brand new friend and a colleague who I've followed for a while. His name is Ryan Smith. Ryan is the part of the team that developed a really cool, cutting edge, and I mean way cutting edge, biological age test. And he's working very diligently to bring the best science to market. And we're going to dive all into that test today. Ryan, welcome, man.
Yeah, thanks so much for having me, Dr. Sherwood. I'm happy to be on.
So we're going to get right into this. So first of all, people are like hearing the word biological age testing. So what is biological age testing anyway, and why is it important?
Yeah, so in a short sentence, the biological age is how old your body is, there are a lot of different ways that people have traditionally calculated this. But for the first time ever, there's been some serious developments in having a really, really good measure of biological age. People have been doing this since the 50s with really crude metrics. But now we're able to do it really, really precisely. We're actually able to predict someone's chronological age and the age of the body. And the reason that that's important is because aging is the number one risk factor for all chronic disease. And so I know one of your mission statements, as we've talked about earlier, is to prevent diseases that you can prevent, right? And to reduce medications as well. And so I think that this is exactly what this helps us do. By knowing our biological age, we can manage our age, the age of our body, and therefore reduce the risk of all of those chronic diseases. And those things are going to be things like cardiovascular disease, diabetes, cancer risk, osteoarthritis, Alzheimer's and Parkinson's. Some of these things are definitely delayable and preventable. And one of the ways you can do it is by looking at this biological age metric. People might be saying, hey, I've been doing the lifestyle stuff. I've been doing all this stuff that I know is preventative anyway. Why do I need this metric? And the answer is that, this metric is by far the best biomarker. You can take any other biomarker from your body. You can look at, your blood levels. You can look at all these other things. And all of these things are necessarily not as predictive as this is. This is and that's the reason this is so exciting. Dr. Horvath from UCLA is one of the people who pioneered this in 2013. And I think he'll win a Nobel Prize for it because it is so inextricably linked to the aging process itself. For anyone out there who's interested in longevity or just reducing the risk of disease, this is a really interesting topic.
It's interesting because we have a saying here that I don't want to live like this, which is kind of the inverted bell curve, but I want to live like a rectangle. We can't help you pick your parents, so we can't help you with chronology either, but we can help you with biological age. And Ryan, how is this biological aging test? How do you analyze this? What's the principles behind it?
Yeah, so it's a pretty complex test that involves really two basic concepts. One is that what we're looking at is a biological metric, what it is DNA methylation. This is an interesting concept because DNA methylation is one of those things that most people don't know about. It generally is in a field called epigenetics, and epigenetics is stands for above the genome. So these are things that happen to our DNA to affect how our bodies act. One thing I always like to say is every cell in our body has the same DNA. Our heart cells and the cells in our eyes have the same DNA, but what makes our heart cells and what makes our eye cells? And the answer is all of these epigenetic changes, genes which are turned off and on to give what they call this phenotype. And the phenotype is what the end expression is, what you see clinically, what you see, happening. And the epigenetic changes sort of control that. Methylation in particular is happening all over the body. And generally it's associated with turning off certain genes. So that's sort of what we're measuring. We're measuring methylation all over the body. There's over 26 million spots on the DNA, which can be methylated. And for what it's worth, 60% of those things are changeable, which brings us to one of the most exciting things about this testing, which is you can actually do something about it. Unlike genetics, which you're sort of self-programmed with, you sort of you can't help those things. Dr. James Watson, who was one of the people who discovered DNA, he was afraid to know his ApoE4 variant, which is a variant for Alzheimer's, for those of you who don't know, because he said, why would I want to know it if there's nothing I can do about it? And, even though obviously he was a great and famous scientist, he didn't know that we had so much control over some of these changes. And finally, we're now seeing that not only can we control it, but we can find out what else controls it, what types of diet and nutrition, and all of those other important things can actually help us make an impact.
So Ryan, this methylation process, for those of you that don't know, it's a process of putting this methyl group onto a strand of DNA, much like a paper clip, if you will. And so, Ryan, is it true that these methyl groups will sort of signal, depending on where they're placed, a start or a stop of genetic transcription?
Absolutely, yeah. This type of methylation is really occurring at one location, and it's generally called the CPG regions, which are repeats of a cytosine, a phosphate, and the guanine. So, those 4 bases that make up DNA, 2 of those repeated over and over again is generally where these things are methylated. And these are called CPG islands. And the interesting thing about these is that most genes have what they call a promoter region. And that's the region where genes promote transcription. So if you have a gene that encodes a protein to give you, black hair, for instance, that whenever that gene is turned on, you're transcribing that gene. And what happens with methylation is that in the beginning of those promoter regions where things would usually go to activate it, if there's a methyl group added, which is just a group of carbons, what happens is it sort of turns off transcription in that area. And so there's a lot of these places in the genome, as I mentioned, and there are 2 different things. One is how we actually measure those methylation. The other one is how we interpret what that methylation means.
Now, the interpretation is very, very key that I want people to really understand, because it's all about context. You
Absolutely.
can't. For example, and we won't go into this today in detail, but we have people come into our office all the time, and some of you out there listening, you probably have been a victim of this, is the dreaded disease called MTHFR. It's not a disease process. Everybody has that enzyme, and everybody has variations of function of that enzyme, and very people have cofactors that make that enzyme work. But the bottom line is we all methylate, don't we? And it's all about the production and placement of these methyl groups that sort of promote activity. Now, this is important to different disease processes, right?
Absolutely. Yes. I mean, obviously the methylation in particular is a big topic, because I think it's something around 60 or 70% of people have an MTHFR gene, which might affect their ability to methylate. And your ability to methylate these genes is often associated with disease characteristics. If you were to measure the 26 million spots of methylation and then correlate that to certain disease outcomes, you can get very, very predictive analyses. For instance, you can say at the 15 million and 336 methylation spot, whenever that's methylated, most people who have that methylated have diabetes, for instance, or cardiovascular disease. And so what you can do is out of all of these different variables, start to correlate what is and is not methylated with outcome variables. And that's where you get what they call these algorithms, which look at all those data points and then synthesize it into something that's clinically useful. And that clinical usefulness is saying, hey, what is your risk for XYZ? And then the secondary part of that is looking at, hey, what changes that methylation value? Is it diet? Is it exercise? Is it some type of supplement? Is it some type of medication? And what we can start to do is start to augment risk by knowing what exactly we need to do. I always like to highlight as well that this is a very, very specific process. It's incredibly accurate. For instance, in clinical, what they teach in med school right now is that one of the best ways to look at diabetes risk is to look at fasting insulin levels and HbA1c, which is glycosylated hemoglobin, and already with methylation, there's actually one marker in the genome. If it's methylated, you're much more likely to develop diabetes in the next 7 years, and so much so it's actually more predictive than the standard of care in medicine. And so what you're going to start to see is, just like there was a huge boom in genetics that led to things like 23andMe and Ancestry.com, you're going to start to see a similar boom in epigenetics, where we're able to look at that as almost like a diary of our life, where what is methylated tells us something about how we've lived or what might happen to us. And so I think that diary is going to, with all this new clinical research coming out, we're going to start to be able to read that diary a little bit better. We're going to be able to say, oh, this is what this means, and this is what that means, and this is what we can do about it.
And it's true, Ryan. I'm gathering. I think I know the answer. You can just confirm for our listeners that some of our inherited sort of epigenetic markers come from our heritage, our mom, et cetera, upon birth. So, if I heard you correctly, that might be the 40%, for example.
Absolutely.
But then there's 60% that are sort of adaptive, or perhaps able to be adapted with this epi or environmental sort of nutrigenomic change. Would that be correct?
Yeah, absolutely right. And I think that the 40%, although it's unchangeable, it's still very important. I always talk about context, right? We have some people who are amazing patients who do everything the right way. And unfortunately, they're still a little bit older biologically than they are chronologically. And the reason being is that 40% is still a large proportion of what you're stuck with. And so one of the things we always like to emphasize is try and get that number as low as possible and compete with yourself. Don't necessarily be too tied up about how big that number is. Just try and get it lower. That's what we traditionally say. And for what it's worth, that 40% also has some really cool attributes in it. It's responsible for things like instincts in animals, where they this genetic imprinting that allows bottlenose dolphins to swim, and bees to locate the hive and other things like that. And so that 40% being locked is not necessarily a bad thing, but it is something that adds context to how we view this whole system.
I think it's fascinating because this, to me, and a lot of people would perhaps be like Dr. Watson and say, I don't want to know. But instead, it's extremely empowering, isn't it? Because it gives you just other metrics, other tools that are measurable. And I appreciate what you said, Ryan, about the competition with self, because we look at these other biomarkers such as serum markers, and they're in these sort of ranges. And somebody would say, well, Ryan Smith, you're normal. I don't want to hear that, because it's a bad contextual statement I just made.
Exactly.
I want to be optimal compared to what I can do. So that's what you're talking about, correct?
Oh, absolutely. And I think that that is exactly why we're seeing this shift in medicine, which is, in my opinion, long overdue, where people are considering aging itself as a disease process. And, and because it's so highly related to all of these diseases, if you can delay aging, why wouldn't you? Why wouldn't you want to be optimal and increase your health span and increase your lifespan? Because like you mentioned, and you don't want that up and down curve. You want it to be, you want a better life while having a longer life. And I think that the cool thing about this is you can accomplish both at the exact same time by controlling this aging process. And so I completely agree. I think that that's one of the most exciting parts about it is this whole normative range isn't necessarily hugely applicable if you can start to change things and put yourself, as high up as you possibly can.
So there's two questions I have that I'm just kind of sitting here thinking about. Number one, obviously, your comparative database that you're getting your algorithm development from, I assume is continuing to grow. That's part one. And then part two would be the $1 million question, or perhaps $1 billion question, is, can biological age be reversed? So just take those questions to part one and then two.
Sure. Yeah. So our data is continuing to grow. And because, the majority of the people who are interested in this testing right now are people who are already a little bit involved in their own health, and being, you can't have that necessarily be the normative population either, because, a lot of the people who are interested in this test are already doing a lot of things to improve themselves. And so we're doing a lot of things to expand that database to people who haven't done a lot of interventions and who represent a large number of groups, whether it be racial groups or socioeconomic groups. Or we want to, and this is something that the genetics interpretations also had to deal with, because the majority of genetic studies were done in places of high socioeconomic status, places like the Western world or some places in Asia. And so we don't want to make that same mistake. And we want to gather a lot of different data from a lot of different individuals so that we can get algorithms which are very predictive and make a lot of sense. And so we're trying our best to do that. We're doing some studies with a couple of universities, and we're doing a biobank study, which we're really, really excited about, that measures things over time. So we can even track outcomes across a lifespan. And so we're really excited about all of those. And then to answer the second question, this was my fundamental question. I think that I've talked about it a little bit before, but I was always interested in this as a cool scientific tool. I never thought it was super clinically helpful. Before last year, actually this time last year, they were using this in different applications, like trying to date the age of refugees to see if they were applicable for asylum, or trying to see how old a person was at a crime scene investigation, or even predicting deaths so that they knew how to charge them for insurance. And all of those cool things are interesting techniques and really cool, but they don't necessarily have a healthcare implication. And I think that my philosophy changed around this time last year when they published a trial called the TRIM trial. And this is really the first study ever published, which showed that yes, absolutely, you can reduce your epigenetic aging rate and therefore extend lifespan and health span. And what they used in that study were a couple of interesting products, metformin, growth hormone, and DHEA. And in just 1.5 years, they were able to reverse aging in 9 patients by on average of 2.5 years. And so that's pretty exciting, because the implications of that are phenomenal. One statistic I always like to share from another leader in the space, Dr. Morgan Levine from Yale, is that if you were to reduce the aging rate by 7 years across the population, you actually cut disease in half. 50% of people are no longer sick. And that is incredible to think about. If you could save 50% of the world from being sick, why wouldn't you do it? And if you, in 1.5 years, you can get a good proportion of that, imagine what you could do over a lifetime. And so that's really what spurred me to get involved and to try and get into this as much as possible, to see what interventions are changing this metric the most, and so that we can make this knowledge available for everyone, and that they can live better and healthier lives.
Now, on that note, as for those of you that want to dig around, you can find the TRIM trial. It's TRIIM. And on that one, Ryan, it just want to educate people. They were talking about, generally speaking, a thymus rebuilding process that's very applicable for today. Just go figure. This thymic, or this immune sort of improvement, or maybe even more youthfulness. Can you kind of go into that a little bit, if you know?
Yeah, definitely. And actually, the narrative is very similar to this whole normative optimization narrative we talked about earlier, where being in the normal range isn't always the best thing for you. And because as we get older, we undergo a process called immunosenescence. And one of the biggest immune organs in our body, our thymus, slowly starts to shrink and become less involved in our healthcare, which is why you see people who are older being a higher risk for COVID-19 or a higher risk for flu and seasonal deaths. Is why they recommend you get those vaccines for flu every year, is to protect those populations, because their immune systems aren't working the same way the majority of ours are. And so the idea with the TRIM trial was, how can we rejuvenate this thymus tissue to have a better immune system? And there are a lot of ways to measure this. In the study, they used an MRI imaging technique to look at thymic fat-free fraction. And that's sort of a measure of how big the thymus is and how well it's producing. And what they saw was that growth hormone was able to regenerate that thymus, and therefore improve the immune system, and then have an effect on epigenetic age. And there are a lot of reasons why that is, but ultimately it's what's represented in your bloodstream. The DNA that you're actually finding is coming from now cells which are younger, healthier tissues. And so it's a good surrogate measurement. And the other part of that trial standing for insulin mitigation, and that was where the DHEA and metformin was used for, is to counter some of the side effects that often might happen with high dose growth hormone. And so that was sort of the whole package. It was sort of, how do we do thymic rejuvenation, improve the immune system, but manage any type of negative consequences? And as you and I, Dr. Sherwood, have talked about as well, there might be some other ways to do this in a better way. And we're investigating, hopefully, that in the near future, and hopefully we'll have some good things to talk about.
And we will, ladies and gentlemen. Just stand by. We are something up that's very, very cool, cutting edge. As far as I know, it's very unique in the world right now. So Ryan and I and the rest of our teams together are going to come up with something that's really neat, and I think it'll be potentially highly exciting for the world in general. Now, Ryan, when you talk about this whole biological testing and all this, and the epigenetic sort of environmental impact on that, you've been doing this for a while. Have you seen impact, clinically speaking, in the person that you know about? I know you deal with a lot of physicians, a lot of clinicians, and a lot of populations. Tell us kind of what you've seen.
Yeah. So I want to preface it by saying we haven't done any huge data analyses yet. We definitely hope to in the future and come out with a lot of things to sort of show trends. Anecdotally, though, we have seen that certain things move this metric more than others. One of those is something we've already talked about in terms of the immune system. Anything which will improve the immune system and change the composition of those immune cells in the blood. So making less senescent T cells, more naive T cells, more plasma B cells, those have a way to reduce this epigenetic aging rate. And so we've seen things, anything that would increase the immune system, a lot of things like with the growth hormone secretagogues, thymus extraction peptides, things like even vitamin D and zinc have an effect on reducing that biological aging process. And then one of the other interesting things that I think is very, very exciting is that there's about to be a couple trials published on just nutrition and how nutrition can affect this metric. And the really interesting thing about the nutrition component is that these things happen very, very quickly in time. As we mentioned, the TRIM trial had been the only trial published to date, and that was over 1.5 years, which is a relatively long time. The diet and intervention studies, which are about to be published, were done in just 8 weeks and able to reverse epigenetic age around a year. And so what we're starting to see is that maybe nutrition is a really not just a big mover, but also a quick mover of some of those things. And so, and the types of nutrition we're seeing things like, methylation diets, which are probably a whole nother conversation. We're seeing things like fasting and fasting mimicking diets being really, really applicable. And one thing that we've seen in the epidemiological clinical literature is things like Mediterranean diets are very, very helpful. Things that, encourage, some type of fat, but also low glycemic index type things.
So it's interesting, and I just want people to sort of start gathering the story here. Number one, we can test sort of methylation status, if you will, through blood markers with perhaps different biomarkers within the methylation capacity, such as S-adenosylmethionine, S-adenosylhomocysteine, methionine, and even homocysteine, and that ratio there helps. But then you're talking about the actual expression of that action, where these methyl groups are placed, and I think you said on the CPG islands. And so epigenetically, Ron, I guess you're saying we can change the methylation expression, and therefore that would potentially change the methylation status on the CPG islands, and then therefore we could potentially, and I don't want to put words in your mouth, we could potentially lower that disease risk specifically in our life. Is that all true?
That absolutely. I think that is theoretically true. And it looks like through the application of these trials, we're seeing that it's not just theoretical; it is even practically true. And one thing I also like to note is that the really interesting thing, and the reason this is probably the most exciting, is that a lot of the markers and methylation places that we look at in the DNA for these things like biological aging. They're not, it looks like as more data comes out, it doesn't look like they're just correlated with aging outcomes. It looks like they might underlie the reason we age. And that's an important distinction because it if we can affect those locations, then we can really affect the aging process itself. And so not only can we do exactly what you talked about for specific diseases, but it looks like we might even do that for aging, which has a lot of different implications.
Well, and certainly, I believe that there's a new ICD-11 code called aging that's coming out. It's kind of cool from the clinician. Yeah. And then you talk about the idea, and I want people to get it in context again, very important. Association does not equal causality, and causality does not always equal effect. But we're talking about really graduating towards this cause and effect process, right? Which really is what we want to do with the increase of data and analyses, right?
Exactly, and that data is coming in a fast and furious way. Yeah. This is something that didn't have much data, at all 10 years ago, and now we're seeing probably new studies published on a daily basis, which link to all these different disease risks. I often like to talk about even the application to cancer, because it's a really exciting area even within this, where there's a ways now to detect stage 0 cancers before any other imaging and any other technique. And the way that they do that is through epigenetic signatures. They take a blood and then they look for these epigenetic signatures. And so that hopefully shows you the level of specificity and precision that this type of testing has, and just how it can affect disease process. If you can find stage 0 cancer, imagine what you can do to treat cancer early versus waiting till you're stage 3 or 4. The implications for that are much longer lifespans and healthier people spending more time with doing the things they love.
Well, it's fascinating because, people probably are listening to this. We use this test here at the Functional Medical Institute. So it's something that Dr. Michelle and I have done on ourselves. And as I think you can appreciate, Ryan, we never will ever do anything patient-based unless we're willing and are doing it ourselves and have done it, because I just think that's certainly hypocritical to its very core. But this is cutting-edge stuff, Ryan, right? And this is like the future that we're just starting to sort of find another galaxy, if you will, right?
Yeah, absolutely. And we've talked a lot about the preventative nature of this, right? Which is great because it helps, it fits exactly in with your mission. The other interesting part about it, though, is it's so personalized. Yeah. And this is a thing that, people have been talking about personalized medicine for a long, long time, how to make individual decisions based on you instead of just following a protocol that is sort of the standard of medicine. And the interesting thing about this is that you can do a preventive medicine approach in a way that you couldn't in a long before. For instance, you could give yourself a medication and then in 12 weeks, look at how that particular medication affected your risk of cardiovascular disease or your risk of Alzheimer's or some of those other different disease states. And you can really vet these therapies in real time. Traditionally, that type of investigation would have had to have been a double-blind, randomized, placebo-controlled trial that looks 40 years at what outcomes happened to these people who were taking the medication over this time. And so what you're starting to do is really shorten that length of investigation by using all this objective data. It's obviously the subjective is very, very important clinically, but now we also have an objective point which allows us to have a conversation and do a personalized medicine approach in a short amount of time, which is invaluable to medicine.
Well, I just love this because it just is really exciting. It's what we needed to do a long time ago, and now we're starting to see a few pioneers such as yourself. And my congratulations and honor goes to you for having the guts to step out there. I know there's other clinicians around the world too, and pioneers like yourself, Ryan. What does this look like? Maybe 2 or 3 years from now. What just in your big dream, what do you see happening?
So I think that this, as I mentioned, I really do think aging itself is a disease and should be classified as one. And so I believe that this will be an instrumental part of a yearly or bi-yearly evaluation of people, and also been used to look at what diseases you're most at risk at. And we already know, through the familiar history, through social histories, that some people are predisposed to these conditions. So let's target them early. Let's stay ahead of it. Like I said, I have an ApoE4 variant. I want to know how to reduce my risk of Alzheimer's. And if I can determine an epigenetic link which helps in that, I absolutely will. And try and use that to benefit my own health process. And so there's so many different ways that this can go. I think that what you'll start to see are things like personalized diet and nutrition programs, which are based on your epigenetic profiles to reduce risk. You'll start to see medication developments. There's actually already now some FDA-approved drugs which work on the epigenome, mostly in cancer, to sort of change the expression of these cancers. So you're going to start to see targeted medications, which probably have less side effects and are more specific. And so you're going to start to see improvements in therapies. You're going to start to see improvements in how we treat our diet and nutrition. You're going to see even recommendations on the best fitness activities to do based on your own individual profiles. And so this is going to be growing at an enormous rate, and having someone to make use of that data is going to be really, really helpful, which is why the physicians are so important in this, especially as it's so new. You really need someone to sort of counsel and guide based on what the data says and the strength of that data. As we're talking a lot about, biostatistics and informatics, it oftentimes can be a little confusing. And so you really need someone to say, hey, at the end of the day, this is what I recommend because of this data. And I think that we're lucky enough to have partnerships with a lot of great physicians like yourself who are helping us communicate that to patients.
Well, certainly, from our perspective, as we were talking prior to our call today and jumping on here, is, our mission is to put this in as sort of a biannually assessment and see it grow and analyze, objectively and subjectively, and then add to the database, of course. And I think you said something very key that I want to affirm, as I agree with you. It is extremely important to have someone in your corner that is trained and understand this to help you interpret it, because information is only as good as the interpretation. And if you get information and don't put it into action appropriately, it will become misinformation. And we've seen probably a ton of that with methylation, I guess, right?
Exactly. And there are a lot of ways to go wrong, which is why you need it centered well.
So Ryan, what are you working on, man? You for those of you that don't know, Ryan is an expert in peptides, and this new TruAge testing. What's new for Ryan Smith? I mean, what's on the horizon?
I'm lucky enough to be, living, doing work, which is always incredibly exciting to me because, this is I think the future of medicine, and I believe in it. And so right now, one of my biggest focuses is looking at these interventions with obviously, trials like ours and doing some other interesting things in the space, looking at things like senolytic medications or plasma apheresis or stem cells or exosomes, and looking at how all of these things can affect the aging process, but in an objective manner. I think that we all, in this field, we've all seen anecdotal results, and that's great. But let's put, let's prove it. Let's go out there and put some data behind it that makes these things more widely accepted and makes us know a little bit more about how exactly they're going to work. And so that's really right now what I'm trying to pour most of my time into is giving everyone not only the tools to see what their age is, but also know exactly what to do once you see that.
Ryan, I would tell you personally, reason I wanted to have you on too, because you're an encourager as well, and I appreciate that. So the people out there right now, and you got your best. Okay, so in 30 seconds, can people get better with their health? Encourage them, Ryan.
Yeah, absolutely. It is entirely in your hands. That doesn't mean you're not behind the eight ball, right? Some people are genetically and have dispositions which might be hard, but it doesn't mean that you can't overcome them. And now I think we have data that's proven and should be at least a mental uplift to say, hey, take control and do the things you need to live the lifestyle you want. And I think that with health underlying everything we do, it is a fundamental part of a healthy, of a nice and enjoyable life. And I think that hopefully that can be the motivation for people to know, hey, it is something I can do. I can be better. Let's try and do it.
Amen. Well said. Second that motion. Ryan, thank you, man, for coming on today. I thoroughly appreciate it. On behalf of myself, Dr. Michelle, and the rest of our team here at FMI, we are sincerely looking forward to working with you more and more and more in the future. And man, let's change healthcare and let's change our trajectory of our health, right?
Yeah, absolutely. It sounds great. Now, I look forward to being back on after we talk about the results of our study.
You betcha we will. So, folks, thank you for joining us today. Another edition of Healthcare's Missing Link. And make sure that you always subscribe to find out who and what is coming next. Remember, don't let those things that are hidden steal your best health. We'll look forward to seeing you on the next edition of Healthcare's Missing Link. Bye for now.